Okay, 6.8. 6.8 is analyzing graphs of polynomial functions. And so, what we're going to do today is we're going to talk about taking polynomials and actually making some rough sketches of what it would look like on a graph. So there's some things that we need to talk about. Remember, what we have here is letting f of x be a polynomial. This is standard form. Highest exponent, so keep subtracting your exponents until you get down to a constant, which would have a 0 exponent. Okay? And it says the following statements are equivalent. So that means they're the same. And it says that you can have a 0. And we've been talking about zeros and solutions. A 0 is a number that when you place into a polynomial, it ends up making it 0. The thing about it is, we've also all along said, hey, solve the equation. What do you mean by solve it? It's where put a number in that makes it 0. So therefore, a 0 is the same thing as a solution. And we end up finding that a solution is actually where it crosses the x-axis. So therefore, it's also x-intercept. The really cool thing about it is the fact that because it's an x-intercept, because it's a solution, and it's a 0, I can actually write them as factors. So therefore, if k up here on top is a 0 of the function, k is a solution, but then I can write it as x minus k as a factor. And we did that just the other day when I said, hey, given these roots, and roots might be another one we want to put on here. So on the bottom, put roots. Roots are a part of this too. They call the roots the solutions or the zeros of the function. We were given roots the other day, and we had to write the actual polynomial. What did I tell you to do? Set them equal to x. Bring them to one side. That created the factors that you multiplied together to make the polynomial. So, on top of knowing all of that information, let's go back to that one chart where if we had a degree, then we had a positive coefficient and a negative coefficient. Let's talk about those shapes. So maybe put above this, put shapes. We didn't have this in a video because we did not record before this. But some of the common shapes we talked about were degree 1, 2, 3, 4, and 5. Okay? And I'm going to move, or get this moved over. I didn't realize, that I have more room here. So positive and negative. If it's the first degree, it's linear. It's a line. That means if it's a positive slope, it goes like this. If it's a negative slope, it goes like that. Right? We talked about that. We should know that. It looks like these graphs are going to be kind of squished together on here. But we also know that if it's a second degree, it's a quadratic or parabola, and it has a what shape? A U shape. And remember, if A is positive, or your leading coefficient is positive, it opens up. If it's negative, it opens down. We also talked about third degree or cubic, and if it's a positive, it looks like an N shape. It starts to have a couple more curves in it. Or if it's negative, it has an upside down N shape. And remember, there was a pattern to these. They really kind of just follow whatever the first degree and second degree does for N behavior. Now we're going to go a little bit deeper and say, what's happening in the middle? Fourth degree, it's a W shape or an M shape. Positive W, negative M. And a fifth degree starts low and ends high, but it has 4 changes in it. So what the rule is, to figure out how many changes there are, think of first degree. First degree has how many changes? None. Second degree has 1 change. Third degree has 2 changes. Fourth degree has 1, 2, 3 changes. The rule is the number of changes is always 1 less than the degree. So if I had a 10th degree and it's positive, it's going to follow that both ends are going to be up, right? Because it's even and it's positive, but it'll have 9 changes on the way to get to the other side. That's what we're trying to get at with this picture here. Now, I'm also on this slide going to highlight the fact that we have something called the relative max and a relative min. First degree does not have a relative max or a relative min, but every other one has a hill or a valley, right? Your graph tops out someplace and it bottoms out someplace. And so, if I was looking at just the quadratic ones, this right here, that point at the very bottom of that valley we'll call, would be called a relative min, right? I put relative min. Where the point way up top here would be called a relative max. Actually, for a quadratic, that would be the max and the min. But for the rest of them, every single one of these, like on this one, that's a relative max. So maybe that might be a better option. Because these numbers over here go up to infinity. There's no maximum to that problem. So we have a relative max because in the middle of things, that's your highest number. It's a turning point. Those turning points are relative maxes and mins. Okay? Any questions to that? The next thing we need to talk about is what happens when we have factors. And what happens when we have factors that have a 1 on it? What happens when my factors have a even on it? And what happens when my factors have an odd number bigger than 1? Because obviously 1's odd, right? But what happens if it's 1, it's even, 2, 4, 6, 8, what do we appreciate? Or a 3, 5, 7, and so on. Because this affects what happens. Now remember, we talked about factors are solutions, which are zeros, which are x-intercepts. So we're talking about what happens at your x-intercepts. So maybe at x-intercepts as a title. At the x-intercepts, what's going to happen? I'm going to put in words, and I'm going to give you a small little picture to show what happens. On the first one, it passes through. When the exponent is just a regular old 1, the graph will pass through the x-intercept without any hesitation. They'd be like, yep, I know I'm supposed to go through. So what does it look like? Well, say we have this point right here. There's your x-intercept. It's got to pass through that point. If it's a first degree, the graph very well could just right through from the bottom to the top. It also could come from the top and go straight through to the bottom. That's just passing through. If you think of a line graph just passes through your x-intercept, right? Now, if it happens to be an even power, it bounces. Now, what do I mean by bounces? It means that as I'm approaching this point, it realizes that, wait a minute, I can't cross this line. And so as it comes in, it bounces. It hits the point and turns around. Okay? Same thing can happen from the top. So we'll go to a different color, and I could come in from the top and bounce off again. So I'm either on top or on below, but I end up having to stay there. It bounced back. And the third one, if it's odd at all, it's going to pass through. It passes with, though, hesitation. It passes with hesitation. It hesitates before it passes. It's kind of like the person who's a little unfamiliar. Do I actually get to go or not go? And so as they get to that gate, they kind of hesitate a little bit, and then they kind of run through. Okay? So we don't know if we can make it or not. So what does that look like? It looks like, okay, same x-intercept is there, but if you're kind of hesitant on knowing if you can pass through a gate, right? You don't know if it's open or not, right? Are you going to go full charging at this gate? Probably not, right? You're going to kind of try to kind of run at it at an angle that if all of a sudden you realize it's not open, that you can quickly get out of the way. So this is what happens. This point is going to come in on the same approach as it looks like it's going to bounce. So he's leaving himself enough space here that he could bounce out of this thing so he doesn't actually have to hit the wall. Okay? But all of a sudden he gets up to the wall and says, oh, gate's open. And he passes through. Now this could happen coming from the other direction, from the top. As in, I could come from the top, hesitate, and go. Okay? I don't know if in football, is that called a hitch and go or something? Kind of hesitate a little bit, kind of go. But this is when the power is odd, bigger than 1. You see a little bit of hesitation. It almost looks like a parabola where someone took a hold of one of the sides and bent it to the other side. Kind of has a nice gentle flow to it. That's what's going to happen with our x-intercepts. So what I want you guys to do is I want to have you make a quick sketch of this problem. It's not going to be perfect. If we took out some a graphing apparatus like Desmos, we could definitely make this work for us. We can put it in. We'll have exactly everything perfect. All I'm asking you for now is make sure you have your x-intercepts in the right spot, your y-intercepts in the right spot, the right shape, and make sure you correctly pass through your x-intercepts. So let's kind of list those things again. So, number 1, I want you to find x-intercepts. Number 2, I want you to find the shape. Number 3, I want you to find the y-intercept. 4, I want you to graph it. Those are the 4 things I want. So, find your x-intercepts. Wait a minute. To find x-intercepts, guys, you take your factors and you set them equal to 0. So, x minus 1 equals 0 and x plus 3 equals 0. Hopefully, you get to a point where you can just look at it and say, hey, x minus 1, the answer will be what? 1. X plus 3 will be -3. So that means that you have your x-intercepts. And when I go to graph it, I need to plot these. So actually, as I go, I'm going to plot these. So I make myself a graph. -3 and 1. So everybody can plot their x-intercepts. I also want you to find the shape. What degree is this? What degree would this polynomial be?
Second.
It's not second. It's third.
Why?
Yes, why is it to the third power? What's the degree of the first intercept? What's the power on it? Second power. Guys, would you guys realize that if I was to put this, FOIL and multiply all this out, I would have x squared. And then an x squared would have to be multiplied by this x, And x squared times x is x to the third or x cubed. So therefore, this is of degree 3. Is the leading coefficient or the leading thing way out front positive or negative? It's a positive x squared times x, which is positive. So we know this is a positive third degree. What shape should it look like? It should look like an N, right? So now we have a shape. We should find our y-intercept. That's pretty easy. How do you find y-intercepts? All y-intercepts are on this line right here. They all have what in common? X is 0. So can't I put 0 in for x here? And if I do that, I'll be able to find my y-intercept. So way down here on the bottom here, I'll do the work. 0 minus 1 squared times 0 plus 3. That's negative 1 squared. Negative 1 squared is 1?
Yeah.
Times it by 3?
3.
It's 3. So it means your y-intercept's at 0, 3. Okay? Has anybody got questions on that? We found the y-intercept by plugging in 0.
Wait.
Now we can graph it. This is where it's going to have to bounce, it's going to have to pass or hesitate. Now, on going back up to our x-intercepts, they had different exponents on them. 2. X minus 1, or the x-intercept at 1, had a square on it. That's even. That means it will do what? All even exponents will bounce. 3, on the other hand, or negative 3, had an exponent of 1. And that's just going to pass. Okay. Now, I'm going to use the idea that the shape needs to start way down below, right? Negative infinity, and come up. And then it's going to do a little bit of squiggling around and end up going back to positive infinity. So that means way over here on our graph, it's got to start down here. And as I get going, I have to pass through that x-intercept.
So it's like,
Is it going to pass through that negative 3, hesitate, or bounce? Guys, really?
it's going to pass through
It's going to pass through.
to go to the next one, and then that once you go up, you're going to go down right away.
It's going to go back down. And when I get to 1, I'm going to bounce.
I knew it.
And there's your end shape. That's what I'm going to ask you to do.